All right, AGS 1. Today we're going to talk about the laws of exponents. This is sort of a pre-lesson to 2.4. So next class, we're going to do 2.4. Today is just kind of getting ready for 2.4. We realized when looking at 2.4 that they assume that you guys know the laws of exponents, which you may have seen these before, but we're still going to approach them from a fresh perspective today. Today's essential question: how do powers interact with each other in different algebraic situations? First up, x squared times x to the fifth. So down the road, you're going to see these two numbers. You're going to see the 2 and the 5 and be like, what do I do with them? Do I add them? Do I multiply them? Do I divide them? Do I subtract? It can be kind of hard to remember the rules, and sometimes you can get them confused. So I'm going to show you guys kind of a long method to be able to do this. I call it the expanding method. So, you guys, x squared is the same thing as x times x. So this is x times x. This part right here is x squared. Remember that if you square something, you're just multiplying it by itself. If you raise something to the fifth power, you're telling it to multiply it by itself 5 times. So this is 1, 2, 3, 4, 5. So this side right here is x to the fifth. Now, when I expand it, if you just look at how many total x's there are, you'll see that you have 1, 2, 3, 4, 5, 6, 7. So if we put this back into exponent form, this is x to the 7th. Now, look at what happened. What happened with the 2 and the 5? The 2 and the 5 got added together to get x to the 7th. So, this expanding method is kind of what I want you guys to do if you get stuck or if you need to clarify or figure out if you got the right answer. But this one is definitely x to the 7th. Next up, we're going to do x to the 5th over x squared. So something's going to happen with the 5 and the 2, but if you're not sure, just expand it. So the top is 5 x's in a row. 1, 2, 3, 4, 5. And then the bottom is 2 x's. Now, anytime you have a fraction where there's something on the top and on the bottom, you can kind of cancel it out. So one set of x's cancels out and another set of x's cancels out, leaving us with 3 x's on just the top. Now, I realize that if you still have this in the fraction, that everything's gone out of the bottom. So you can kind of think of it like there's a ghosty 1 down there hanging out. But dividing anything by 1 doesn't really change it. So this is the same thing as xxx, which is x to the 3rd power. Now, that was kind of the long route of expanding it. But if you look back to the OG, what happened between the 5 and the 2? Well, it's anytime you're canceling out sets of x's, it's like you're subtracting those 2 x's out of the bottom from the 5 and the top. So the 5 minus 2 gave us the 3. And we're going to put all these rules together at the end of this. Next up, x to the 5th squared. So it can be kind of confusing about what to do with power of a power. So I'm going to go with the expanding method again. Remember that if you square something, you're multiplying it by itself. So this is x to the 5th times x to the 5th. Then you can expand again and say this is 1, 2, 3, 4, 5 times 1, 2, 3, 4, 5. But then those both parentheses aren't really doing anything, so you can go 1, 2, 3, 4, 5 times 1, 2, 3, 4, 5. So this is a grand total of 10 x's. So this is x to the 10th. So what happened with the powers? If you go back to the OG, the 5 and the 2 actually got multiplied. This is what I call power of a power situation. So if you have powers stacked on each other, you end up multiplying them. Now, this looks a lot like a problem we did in the beginning, where you're like, okay, we figured out that you subtract the two powers, but in the beginning, the top power was bigger than the bottom power. So I want to show you guys what happens when the top power is not bigger than the bottom power. Let's go with the expand method again. So I made x to the third, just 3 x's, and then x to the seventh, 7 x's all in a row. Now if we start canceling out, we have 1 set of x's, 2 set of x's, 3 sets of x's that cancel out, and everything went away in the top. So you still write your fraction, but you write a big 1 in the top. Remember, there's always like a 1 placeholder if everything goes away. But then left in the bottom, we have x, 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 x. So this is 1 over x to the 4th. Now, what if we had taken an alternate route and said, well, jolly, we already figured out that you can just subtract the 2. So this is the same thing as x to the 3 take away 7. Which is true, it is. But if you take 3 and then take away 7, because the 7's bigger, this becomes x to the negative 4. So what I want you guys to see is that negative exponents are the same as putting that exponent in the denominator and making it positive. So x to the negative 4th is the same thing as 1 over x to the 4th. In general, all of these only work if you have the same base. So I'm going to do a couple examples after this where maybe they're not the same base. But notice that when I say the base of the exponent, this is the base and this is the power. So these two have the same bases and you're multiplying those bases. This is where you add those two powers together. X to the a plus b. If you're dividing the same base, you subtract. If you have power of a power, where the powers are stacked on top of each other, you multiply. So this becomes x to the ab. And as it just showed you in that previous example, if you have a negative power, you can go ahead and put that in the basement and make it positive. So x to the negative a is the same thing as 1 over x to the a. Let's do a couple examples. Now, 7 to the 3rd and 7 to the 12th, if you try to punch this out on your calculator, it's just going to be a huge number. So we're not going to come up with the actual number that's the answer. We're just going to simplify. So because those have the same base of 7, you can leave that base. And then because you're multiplying, the multiplication turns into addition. So you add the 3 and the 12 to get 7 to the 15th. Next example, 13 to the 10th over 13 to the 4th. Yes, if you were confused, you could expand these, but it's going to be writing a lot of 13s. So just remember that like some of them cancel out, and this is the same thing as 13 to the 10 minus 4, which is 13 to the 6th. I don't care what 13 to the 6 is, you can just leave it right there. That's a simplified answer for now. Okay, slightly tricky one here. First, because of PEMDAS, we have to do the powers first. So I'm going to let that 2 on the front just hang out, and then that becomes 2 to the 3 times 5. So this is 2 times 2 to the 15th. Now, this 2 out in front, don't forget that any number, when you write it, has a little ghosty 1 up on the top. We just don't write it. So there is a 1 power on things whenever there's like nothing, no power written on them. So this can be simplified further because here, same base, same base. This is 2 to the 1 plus 15, which is 2 to the 16th. Oh, I started boxing my answers. I better do it. Let's do a slightly better example. What should we do now? Okay, so I purposely threw a 3 in here to kind of throw you guys off. Remember that you can only do these power rules with the same bases. So the base of 10 is the only thing you can do there. So this becomes 1 over 3 to the 7th times 10 to the 4 minus 12. So the 4 minus 12 becomes negative 8. So just let the 1 over 3 to the 7th hang out. And you get 10 to the negative 8. Now, don't forget that negative exponents you can throw into the denominator. So I'm going to let the 1 over 3 to the 7th just hang out. And then this becomes 1 times 10 to the 8th. Which you can smush together into one final answer of 1 over 3 to the 7th times 10 to the 8th. All right, you guys, that's all I got for you today. Good luck with the formative.